Hey guys, and welcome back to another A-Level Further Maths revision video. And in this video today we're going to take a look at a Core Pure 2 predicted paper. And like the previous predicted papers that I've put together, this is just built using the topic test that Edexcel have released and old exam questions from the FP1, FP2 and FP3 exam papers. It's worth pointing out here that not every topic of the advanced information is included in this video. There's only a couple missing, such as differentiating hyperbolic functions and the Maclaurin series. There might be one more off the top of my head, but mainly that's kind of what's missing here. But everything else is included in this paper and this video. I hope this paper is still helpful though, and this video. I know Core Pure 1's tomorrow, so if you're sitting that, best of luck. And then best luck next week with Core Pure 2. So that's everything we need to start with. Let's jump into this Core Pure 2 predicted paper. Starting off with the very first question then in our Core Pure 2 predicted paper, we have a question here taking a look at matrices and system of equations. So in part A, we've been given the system of equations, and we're asked to determine the values of k for which the system of equations does not have a unique solution. Now, if we're told this does not have a unique solution, and in that case we need to determine the value of k here, then what we know is if this does not have a unique solution, then the determinant of this matrix here, once we represent this in matrix form, must be equal to 0. So let's set this up as a matrix first. So let's do it up here, part A. So for example, the top row of this matrix here, so this is x minus 3y plus 2z. Ignore the minus 7. All we're concerned about is this part here, so before the equals, that's what we're classing our 3x3 matrix as. Okay, so in that case our top row is going to be 1, minus 3 and 2, so it's just the coefficients of the variables. So I've got 1, minus 3 and 2. For this next row here, again just the coefficients, so that's k, so that's going to be k there. We've got y here, so that's just going to be 1, and then minus z giving us minus 1. And finally for the bottom row we're going to get 6 minus 5, and because this is k minus 1, then we take that as k minus 1. So whatever the coefficients are, we just use them even if they're algebraic. Okay, so that's our matrix here. Now we just need the determinant here, and we're going to set that equal to 0. Okay, and then we're going to solve whatever that is, and that will give us our value of k, or the values in this case. So if I expand along the top row of this matrix here, so the determinant here, I'm expanding along the top row. So remember, this is going to be plus, minus, plus. So it's going to be one lot. So it's going to be one lot here. And again, imagine you cross off this row and this column. So what I get left with is 2 by 2 matrix here of 1, minus 5, and k minus 1. So it's going to give me one lot of k minus 1. So k minus 1 minus 5 times minus 1. Okay, so that's the first part there. We now move to the next element here. So this is minus 3, and normally this would be minus, but because this is a minus as well, it's going to be minus of a minus. It's just the same as adding it. So it's 3 lots now, and we might run out of room here looking at this. So what I'll do actually is I'll just start down here. So we're looking for the determinant. So we've got one lot of what we had so far, so k minus 1 minus 5 times minus 1. That's always the issue with these questions, they take up so much room. So now we have 3 lots, so we're crossing off this row again. So we're always going to cross this row off if we expand along the top row, but this time we're crossing off this column, so I get left with k minus 1, 6, and then k minus 1. So in that case then, this is going to be k lots of k minus 1, so k lots of k minus 1. And now we minus, so again it's this row, this column, so it's now going to be minus 1 times 6 there. Okay, and then finally we move to the last element here. We've got 2 lots, so again we cross off this row and this column this time, so I get left with this bottom left 2 by 2 matrix of k, 1, 6 and minus 5. So that's going to be minus 5k, so minus 5k, and then minus 6 times 1, so minus 6 there. Okay, so here now I just need to start cleaning this up here. If we start up here on this furthest left part, I've got one lot of k minus 1 minus 5 times minus 1. So minus 5 times minus 1 is plus 5, or positive 5. and we minus that. So I've got k minus 1 minus 5. So it's going to give me k minus 6 there. So I get k minus 6. I've got here now, I've got k squared minus k, and then we've got minus 1 times 6. So I'll break this down step by step just so we don't accidentally trip up here. So I've got 3 lots of k squared minus k. Minus 1 times 6 is minus 6. Then we minus that, so that's the same as plus 6 there. And this final part here, I'm going to get minus 10k at minus 12. And again, let's just clean this up one more time. So we're going to get k minus 6 plus 3k squared there. So we get 3k squared. Now I've got minus 10k here, and this is minus 3k, so in total that's going to be minus 13k there. That's going to be minus 13k, and then we've got 3 times 6 giving us plus 18 there. So plus 18, and finally we've got the minus 10k, which we've just put together with that. We've got the minus 12. I'm cleaning this up in quite a haphazardly way. This could definitely be done a little bit neater than I've done it here. But again, let's keep clearing this up. I've got 3k squared. I've got minus 13k plus k here. So that's going to give me minus 12k. And we've got minus 6 minus 12, so that's minus 18, plus the 18, so that's equal to 0. Okay, now this determinant here, we should have set it up here, this is equal to 0, so this is equal to 0. This is equal to 0, and then finally, this is equal to 0. And what we need to do now is just solve this for k basically, and whatever then values of k are, that's what we were looking for in part A. So to solve this now, we're just going to factorise this, hopefully straightforward. Factoring out a 3k, so I get 3k, k minus 4 there, and this is all equal to 0. So this gives me 2 solutions now for k. What I get here is either k equals 0, because we're saying 3k is equal to 0, or k minus 4 is equal to 0, and therefore k is equal to 4. Okay, so that gives us the values of k for which the system of equations does not have a unique solution. So that's part A done there, getting us our first 4 marks to start with. Let's take a look at part B now, and I think part B is actually quite nice if you have a graphical calculator, and I would definitely recommend one if you're doing A-level further maths. Even at this stage, if we're a few weeks off the exams, you will still find it useful. So what we're told here is that k is equal to 5. So we're told k is equal to 5. Now, if k is equal to 5, I can substitute that then into this system of equations here. So what would my matrix look like here? Well, what I'm going to get then in this case, again, the top row will be 1, minus 3, and 2. For the next row here, so this is kx. So if we said k is 5, that's 5x. So that element there will be 5. That'll be 1. That'll be minus 1. And then finally for the bottom row here, I'm a bit short on my matrix, but that's going to be 6, minus 5. And then finally here, this is k minus 1. So if k is 5, 5 minus 1 gives us 4. Okay, that's equal to 4. So that's the matrix that we're working with here. And what we want to do is find an appropriate inverse matrix to solve this system of equations. So what we're looking for at the end is x, y, and z, a value for x, y, and z. So how do we do this? Well, imagine this is multiplied by x, y, and z. That's what we're looking for here. Okay. Now we know this would be equal to minus 7, minus 5, and 1. So we're saying here this is equal to minus 7, minus 5, and 1. Okay. So if I simply want the value of x, y, and z here, then what I need to do now is multiply both sides here by the inverse of this matrix. So that's why it says finding an appropriate inverse matrix. So that's why we're doing this here now. Now this is where a graphical calculator will save you a lot of time. If you don't have a graphical calculator, you've got to go through the long way of finding the inverse matrix here and then multiplying both sides again without a calculator. But if you do have a calculator here, it's absolutely fine to use it. And I'm going to do it as if you do have a graphical calculator here. So what I'll do is I'll write the inverse matrix up here. So the inverse of 1, minus 3, 2, 5, 1, minus 1, and then finally 6, minus 5, 4. So the inverse of this is equal to 1 over 15. And my matrix here will be minus 1, 2, 1, minus 26, minus 8, and 11, and finally minus 31, minus 13, and 16. Okay, so that's my inverse matrix there. So simply now, to get x, y, and z, I'm just going to multiply both sides now by the inverse matrix. So therefore, let's do it in a different color just to make it clear this is the solution. So to get x, y, and z here, and this is equal to the inverse matrix here. That's going to be 1 over 15. My matrix minus 1, 2, 1, minus 26. This gets a little bit tedious. Minus 8 and 11, minus 31, minus 13, and 16. And then we times it by this matrix here. Minus 7, minus 5, and 1 there. And all we need to do now is put this part here, the right-hand side, into our graphical calculator. Okay. Obviously, in your calculator, you'd need to multiply your matrix here by 1 over 15. So, for example, it'd be minus 1 over 15, 2 over 15, 1 over 15 for the top row. But just make sure you input it like that. And if you do this correctly, what you should get here then, for our values here for x, y, and z, our solutions then is we get minus 2 over 15. We get 233 over 15, and finally 298 over 15 there. Okay, and that's our solution there to part B, or part 1 of B. And then finally, we're just asked to interpret the solution geometrically. So you don't need to say too much for this. You just need to understand what's actually happened here. And what we found here then, basically, is that we've got 3 planes. Okay, we've got 3 planes that meet at a single point. So all we need to say is 3 planes that meet at a single point there. Okay. So make sure you do understand what happens when you get your solution. It is very often, or it is very often the case, you will be asked to interpret the solution geometrically. Okay. So important skill. Make sure you're confident with it. But overall, that gives us the solution there to part B and question 1 there. Moving on to question 2 here. We've got a question taking a look at sketching on an Argand diagram. So part A, we're asked to shade on an Argand diagram the set of points, and then again these 2 parts here, and then part B is a bit of a follow-on essentially from part A. So if you struggle with part A, you might find part B quite tricky. Okay, so let's just jump straight into this with part A. So question 2A. So where do we begin with a question like this? Well, we need to recognize what we've been given. So this is split into 2 parts here. I've got this part on the left, the intersection, and I've got this part here on the right. And the part on the left here, hopefully you recognize this is the equation of a circle. And the reason we know that is because we've got this part here. Okay. So this tells us the center of the circle. So the center here is given from this minus 1 minus I. So because this is minus 1 minus I, that means the center is going to be 1, 1. Okay, so that's the center. And then we also need the radius R. And the radius comes from this part here. So because that's 3, we just simply take the radius as being equal to 3. So that's the equation of a circle. We've also got this part here on the right of the intersection. And what does that tell us? Well, that tells us, or what you should recognize this as, is a half line. So this is a half line. So this is a half line. And this starts at 2, 0. Because this is the argument of z minus 2, and we know this starts at 2, 0. So starts at 2, 0. And from here now, we've got everything we need to shade on an Argand diagram, the set of points here that we've been given. So let's have a go at shading this and sketching this on an Argand diagram. Just a warning, mine will be probably not the best. It's quite hard doing this kind of freehand without a ruler. But let's see what it looks like. Okay, so them are my axes there. Remember, this is the real and this is the imaginary. So we know the center, that's 1, 1. So we can plot that point there. Let's just say that's, I don't know, there. And we also have the radius is equal to 3. So this doesn't have to be perfect. Obviously, just trying to make sure it looks sensible. So let's say this looks something like this. So clearly the center's way off, so I'm just going to readjust that. I'm going to take that as my circle, just readjust the center. That seems a bit easier. Let's just say that's there. So we say that's 1, 1 there. Okay, so that's my center. And we've also got the half line starting at 2, 0. So if that's 1, 1, 2, 0 might be here, for example. Okay, so what I've got then is my half line starting at 2, 0. And we need the angles that are given by this part here. So we know the argument of z minus 2 must be greater than or equal to pi over 4, but less than or equal to 3 pi over 4. So with pi over 4, that's just 45 degrees. So that's 45 degrees. So from 2, 0 here, that makes a 45 degree angle. Something that looks like that. Okay. So that's the argument of z minus 2 is equal to pi over 4. And then we've also got 3 pi over 4. So that would be 135 degrees. That's 135 degrees. And that's going to look something like this. And this will actually go through our center. Okay, so it's going to look something like this. Okay, again, these should be straight lines, but I'm doing it freehand, so it's not brilliant, but that's what we're going to get. Okay, and that's the argument of z minus 2 is equal to 3 pi over 4. Okay, and all that's left here then is just to shade on the Argand diagram the set of points. So what we need to be here is inside the circle, but also satisfying this argument here. And the only place that actually leaves us then, if we just shade on the diagram, is here. Okay, so we're inside the circle and in between this V here. Okay, so we get something that looks like this. Okay, so that's part A there. Hopefully not too bad, and part A will definitely help us with part B here. So let's just take a look at part B now. So for part B, we're told the complex number W satisfies these two parts here. Now, if we know it's between part A and part B, the only thing that actually changes is instead of using Z here, we're using W. Same again here with the argument of Z minus 2, it's now the argument of W minus 2. So we can use part A to essentially answer part B. So what we're saying here is the complex number W lies on the circle here, on the circumference of this circle, and the argument of W minus 2 is equal to pi over 4. So that lies on the half line here. And if it lies on the circle and the argument of W minus 2 is equal to pi over 4, then there's only two possible places this could be. And if we do this in a different pen colour, the only possible places it could be here, where they intersect, or if we extend this half line here, it would be here at the bottom, where again it would touch. Now, we don't include this solution here, we want this solution, but when we go on to solve for x, we will get two solutions. Okay, so that's why we get two solutions, and then later on we need to discuss why, or we're kind of saving ourselves why we need to discuss omitting one of the solutions. Okay, so let's carry on then with part B. Well, the first thing we should do here is write down the equation of the circle, write down the equation of the line, and then hopefully what we should be able to do is solve that by substitution. So if we start with a circle, this should be quite straightforward. We've already got the equation of the circle from here. Okay, so writing this in Cartesian form then, we've got x minus 1 all squared plus y minus 1 all squared is equal to r squared. So if r is 3 here, like we said up here, then that's going to be r squared, which is 9. Okay, so that's the equation of the circle. We now want the equation of the line. So that's this line here. And the equation of this line, well, that's going to come from using the fact that we know y minus y1 is equal to n lots of x minus x1. Okay. Well, the point we're going to use here is this 2, 0. So using 2, 0, then y minus y1, which is 0, so we get y is equal to m. Now, we haven't discussed the gradient here, but if we think about this, this is a straight line at a 45-degree angle, so that's pi over 4 there. So the gradient of this line here is going to be positive 1. Okay, for every 1 unit we go across, we would also go up 1 unit. Again, for every 1 unit we go across, we'd also go up 1 unit. Okay, so the gradient here is 1. And all I'm simply going to get then is x minus x1, so that's x, minus x1, which is 2. So I get x minus 2. Okay. And now that we've got this value, this equation of the straight line, I can now substitute this into the equation of the circle. Where I've got y minus 1, we can replace that y with x minus 2. Okay, so if we just cut off pi a and b here, what I'm going to get then is x minus 1 all squared plus, so this was y minus 1, so if y is x minus 2, that's going to be x minus 3 all squared. So that's x minus 3 all squared, and that's equal to 9. So I just need to solve here for x then. So expanding these double brackets here, so I've got x minus 1 squared, so that's going to give me x squared. I'm going to get minus x, and then another minus x, that gives me minus 2x, and then finally minus 1 times minus 1 gives me plus 1. This double bracket here, again, I'm going to get x squared, so I get plus x squared. I'm going to get minus 3x and another minus 3x, that's going to give me minus 6x. And then finally, minus 3 times minus 3 gives me plus 9. And that's all equal to 9. And what we should get here is simply a quadratic equation that we should be able to solve and get a value for x. Okay, and this is where we're going to get our two solutions for x now, like we would for generally solving any quadratic equation. So collecting like terms here, I'm going to get 2x squared. So I get x squared, another x squared, 2x squared. I've got minus 2x, minus 6x, that gives me minus 8x. And then finally we've got plus 1, plus 9, so that's 10, minus the 9 here. So we're going to set this equal to 0 so we can solve it. That's going to give me plus 1. Okay, and that's all equal to 0. Now with any general quadratic here like this, we'd always check to see if it factorizes. It would save us a massive amount of time. Unfortunately here it doesn't factorize, so we need to solve this by either completing the square or using the quadratic formula. In this case, I'm just going to simply use the quadratic formula. This should hopefully be quite straightforward, just using the quadratic formula here to solve this quadratic. So what I get then is x equals a plus or minus the square root of 64, that's b squared, so 64 minus 4 times 1 times 2. Okay, and this is going to be all over 2a, so that's 4. Okay, and then just by simplifying this here, I get a plus or minus the square root of 56 over 4. Well, the square root of 56, we can write that as the square root of 4 times the square root of 14, and the square root of 4 is equal to 2, so I get 2 root 14. And then we can write this here by dividing top and bottom by 2. So I'm going to get 4. So I get 4 plus or minus. So that would be 2 root 14. So if we divide that by 2, we just get root 14. So that's 4 plus or minus root 14 all over 2 there. Okay. So that's our solutions there for x. But remember, we just want one of these solutions. We don't want both. And we need this solution here. This is the one that we need. Okay, that gives us our solution. So we clearly need the bigger of these two solutions, which comes from taking the positive solution. So therefore, x is equal to 4 plus root 14 all over 2. Okay, so we've got the x solution. We now also need the y solution. Okay, so we need the y solution here. Remember, y is equal to x minus 2. So if this is x, then we just replace x here with 4 plus root 14 all over 2, and then we subtract 2. And here, this is 4 over 2 plus root 14 over 2, and then we minus 2. So 4 over 2 is equal to 2, so they just cancel with this minus 2 here, and I simply get left with root 14 over 2. Okay, so that gives us the y solution. And what we've got now is the complex number w. And we've run out of room, so make sure you've just got the x and the y solution here. We just clear everything here. And what I've got for w is our x part here, so that's going to be 4 plus root 14 over 2 plus root 14 over 2. So that's the y part here. So root 14 over 2i. Okay, so that's the complex number w. Now what we want here is in its simplest form, the exact value of the magnitude of w squared. Okay. So simply all we're doing here is taking the magnitude and squaring it. So in that case then, for the magnitude w all squared, that's going to be equal, to start with, the square root. And then we're going to square each term here for w. So that's going to be 4 plus root 14 all over 2. We'd square that term. But we then square this part here for the imaginary part. So that's going to be root 14 over 2 all squared. And because we want the magnitude of w squared, well, if you just wanted the magnitude of w, then this would be correct. But we want the magnitude of w squared, so we're just going to square all of this here. Okay, so we take all of this and we square it. And clearly what would happen here is the square root would disappear, and we're just going to get left with what's underneath the square root. So this is going to be equal then to, right in brackets, 4 plus root 14 over 2 all squared plus root 14 over 2 all squared. And then you can put this into your calculator. If your calculator will give you this in its exact form, then that's fine. If not, you'd have to do it by hand. Remember, you need to give it in its exact form. But given this in its exact form here, what we get is 11 plus 2 root 14. Okay, so 11 plus 2 root 14 there. Okay, so that gives us the solution there to part B and the solution to question 2 overall. Taking a look at question 3 now, we have a question here looking at roots of polynomials. And what we've been given is a cubic equation which has roots alpha, beta and gamma. Now without solving the cubic equation, we're asked to determine the value of 1 over alpha plus 1 over beta plus 1 over gamma. So part A is pretty standard, part B is a little bit trickier, but hopefully you should find this question quite straightforward and hopefully a nice easy 6 marks. So let's take a look at part A first. Where's my pen? There it is. So part A. Now, for something like this where it's 1 over alpha plus 1 over beta plus 1 over gamma, if we think about that, so let's just do that up here just so we know where we're starting. So 1 over alpha plus 1 over beta plus 1 over gamma. Okay, so for something like this, if we think about getting this over a common denominator, what would we actually get here? Well, the common denominator would be alpha, beta, gamma. Okay, the product there, so it would be alpha, beta, gamma. So our denominator is alpha, oops, that's a terrible alpha, beta, and gamma. Okay, and then the numerator, so for example here, this 1 over alpha, we need to times that by beta, gamma. So it's going to be beta, gamma, beta, gamma. This 1 over beta, I times that by alpha, gamma, so it's going to be plus alpha, gamma. And then finally this 1 over gamma, that would be alpha, beta, so plus alpha, beta. Okay, so we know what we need to find here to determine the value of 1 over alpha plus 1 over beta plus 1 over gamma is the pair sum here. So the pair sum, beta gamma plus alpha beta, and then the product here, okay, alpha beta gamma. So we need to determine each one of these individually, but while we're here we might as well determine all of them. So we want the sum, the pair sum and the product. So if we start with the sum then, so that's alpha plus beta plus gamma. Well, remember, that's simply minus b over a. So what's a and b in this case? Well, we use a different pen colour to illustrate this. For our cubic equation, a is the coefficient of x cubed, so a is 3. B is the coefficient of x squared, so b is 1. The coefficient for this minus 4x here, so this minus 4, that represents c, so c is minus 4. And then finally for d here, That's just the last term here, so that's going to be 1. So in that case then, for minus b over a, that's going to be minus b, which is 1, divided by a, which is 3. So we get minus a third there. Okay, so that's the sum. Now we want the pair sum. So the pair sum here is alpha beta. So alpha beta plus beta gamma plus alpha gamma. And notice that's what we've got up here. So what we're doing now is we're finding the numerator that we need. And for the pair sum like this, the way we find that is c divided by a. Okay, so again we just look at our values here. C is minus 4, so we've got minus 4 divided by a, which is 3. So we get minus 4 thirds there. And then finally we want the product here, so that's going to give us the denominator, alpha beta gamma. So we get alpha beta gamma, and that's simply equal to minus d over a. So minus d over a. And like you can see, these are quite straightforward to remember. Just remember that the sum is minus b over a, the pair sum is c over a, and then the product is minus d over a. Okay, so minus d over a, again, we look at our values. So this is going to be minus 1, which is d equals 1, divided by a, which is 3. So we get minus a third there. Okay, so we've got everything we need now. All we need then to determine the value of 1 over alpha plus 1 over beta plus 1 over gamma is to use this formula here. So therefore, 1 over alpha plus 1 over beta plus 1 over gamma is equal to the pair sum, which is minus 4 over 3, so minus 4 over 3. And we divide this by the product, alpha beta gamma, which is minus a third. Minus a third. Well, it's a negative number divided by another negative number, so the negatives will cancel. So what I've got here essentially is 4 over 3 divided by 1 over 3, and 4 over 3 divided by 1 over 3, that just simply gives us 4 there. Okay, so we get 4. And there we have it. So that's the first 3 marks for the value of 1 over alpha plus 1 over beta plus 1 over gamma. Now for part B, we're asked to find a cubic equation that has roots 1 over alpha, 1 over beta, and 1 over gamma, giving your answer in the form x cubed plus ax squared plus bx plus c equals 0. So we do need what we found here in part A, so make sure you've got a note of this if you haven't already. What I'll do is I'll clear the screen now just so we've got enough room for part B. So let's have a look at part B then. So for part B, we're using the roots 1 over alpha, 1 over beta, and 1 over gamma. So what we need to do now to find the cubic equation is we need to obtain the new sum, the new pair sum, and the new product. Once we've got all of those, we can easily see what the cubic equation will be in that case. Okay, so we need the new sum. Now the new sum, we just obtain that from part A. Okay, that's 1 over alpha plus 1 over beta plus 1 over gamma, which we've already worked out. So that was 4. Okay, that's what we said this was equal to. So that's 4, and clearly this is just the sum. So the new sum is 4. Now the new pair sum, how do we work this out? Well, what we're saying here is we've got 1 over alpha beta plus 1 over beta gamma plus 1 over alpha gamma. Yeah, alpha gamma. Okay, that's our new pair sum. So how do we work this out? Well, again, let's get this over a common denominator. If you're ever in doubt, just get everything over a common denominator and see if you've got things that you already know. Okay, so we put this over a common denominator. For example, this 1 over alpha beta, we need to times that by gamma. So that's going to be gamma. So that's gamma. The common denominator here, like we said, will be alpha beta gamma. That's our common denominator. So the first one there is gamma. This one's beta gamma, so we need to times that by alpha. And then finally, this is 1 over alpha gamma, so we need to times that by beta. Okay, so that's getting it over a common denominator there. So clearly what we've got here now is alpha beta gamma. So let's just write that in order just so we can see it clearly. Alpha beta gamma all divided by alpha beta gamma. And we know these from part A. Okay, so alpha beta gamma and alpha plus beta plus gamma, and then alpha beta gamma. So the sum here, that was minus a third in part A. And then the product in part A, again, that was minus a third there. Okay, so minus a third divided by minus a third, well, that just simply gives us 1 there. Okay, so that's a new pair sum. And then finally, we need the new products here. So we need the new product. And just like we did here for the new pair sum, we're going to get it over a common denominator. So it's going to be 1 over, in fact, we don't even need to get it over a common denominator. We've got 1 over alpha, beta, gamma. Okay, and we know what alpha, beta, gamma is. We've already used it in this part here. That was minus a third. So this is 1 over minus a third. So that gives us minus 3 there. Okay, so what we've got now is we've got everything we need to actually find this cubic equation. We've got the new sum, that's 4. We've got the new pair sum, that's 1. And we have the new products, minus 3. So to find our cubic equation, well, it's going to be x cubed. Okay, that won't change. X cubed. Here, we've got minus now. We minus the new sum. So if we said the new sum is 4, this is going to be minus 4x squared. So let me just get rid of that part there, actually. So I'll write that in here. This is going to be minus 4x squared. Okay. Now we move to the x term here, and the x term comes from the new pair sum. So the new pair sum is just 1, so that's just going to simply be plus x there, or plus 1x, but we'll just write that as x, so plus x. And then finally, the last term comes from the new product. So that's just minus 3. Our last term is just minus 3, and that is all equal to 0 there. Okay. So that gives our solution there to part B. So like we said, if we just go back to how we got this cubic, well, we know it's x cubed, so we just get x cubed at the front. We've got ax squared, so the a here, that comes from the new sum. So the new sum was 4, but we minus this part here, so it's minus 4x squared. The next term, this x here, well, the coefficient of that comes from the new pair sum, so that was 1, so it's just plus x. We add this part on here, and this last term is the new product, which was minus 3, so we get minus 3, and that's all equal to 0. So that gives us our solution there to question 3. Moving on to question 4 here, we have a question taking a look at differentiating inverse trig functions. Now what we've been given here is the curve C, which has the following equation. So y is equal to arc cos of a half x. And in part A, we're just asked to show that C has no stationary points. Now, if you're watching this video, you should hopefully be a further math student, and in that case, you should be, thinking straight away, if we're looking at the stationary points, it's going to involve differentiation. Okay, so I'd expect that from an A-level student. Further math, you should essentially just be seeing that straight away. So what we've got here is y equals arc cos half x. So let's just write that down. So arc cos of a half x. And what we need then, if we're looking to show that C has no stationary points, is the differential here, dy by dx, and then we need to set that equal to 0, and hopefully show some kind of contradiction. So let's start by differentiating this then. So that's going to give us dy by dx. Now for this result here, we can refer to our formula book to give us a bit of a hand. And what we've got then is this is y equals arc cos. So we know the result here is going to lead to something of this type. Okay, because f of x here is arc cos x. Ours is slightly different. We've got a half x, but it won't change it too much. But we should get something that looks like this. Okay. Now with ours, because this is a half x, we just need to take that into account then. So when we differentiate here, straight away we're going to get minus a half. So this is a half x. We're going to get minus a half. Now I'm keeping this in the numerator. You can bring the 2 down in front of the square root here in the denominator. That's fine as well. But I'm going to keep it as the numerator for now. Okay, so I get minus a half all over the square root. So it's 1 minus x squared. Now in our case, the x isn't x squared. It's going to be a half x squared. Okay, so we do 1 minus half x squared. Okay, and we just need to simplify this here. So again, we get minus a half in the numerator. This is all over now. The square root of 1 minus, so a half x all squared. I'm going to get 1 over 4 x squared. Okay, so 1 over 4 x squared. So here, what we need to do now, and this is true generally when you're differentiating inverse trig functions, is we refer back to the original equation. So y equals arc cos a half x, and we need to rearrange this so we can get something here in terms of x, okay? And then we can substitute it back into our dy by dx. So if we've got y equals arc cos a half x and we want x, then we need to take the cosine of both sides here. So that's going to give me cos y. So if you take the cosine of arc cos, they just cancel, and I just get left with a half x. So we get a half x. And cos y here is equal to a half x. So in that case, if I want x, I just times both sides by 2. So x is equal to 2 cos y. Okay. And then if we substitute that back in here, well, first let's just square this. So x squared is going to be equal to 2 cos y all squared. And that's going to give me 4 cos squared y. Okay. Now when I substitute that back in here, so I'm going to get minus a half all over the square root. So it's 1 minus 1 over 4x squared. So if x squared is 4 cos squared y, and you divide that by 4, we just get left with cos squared y. So this is 1 minus cos squared y. Okay. And from here now, hopefully, you're spotting something promising. And that's that we've got the square root here of 1 minus cos squared y. So we know now our trig identities, basic trig identities here. Sine squared y plus cos squared y is identical to 1. We can rearrange that then. So sine squared y is 1 minus cos squared y. And then if we've got the square root here of 1 minus cos squared y, then we just take the square root of both sides. So that gives me sine y is the square root of 1 minus cos squared y. So what I've got here then is minus a half over the square root of 1 minus cos squared y, which we've just said is sine y. So I've got minus a half divided by sine y, or we could also write this as minus 1 over 2 sine y. Okay. Now here, we're not finished yet. We still haven't shown that this curve, C, has no stationary points. But we found dy by dx. So this is dy by dx. This looks a little bit messy. Just clear this off a little bit here. So what we need to do now is set our differential here, dy by dx, equal to 0. And if we do that, we get minus 1 over 2 sine y is equal to 0. And what we do now is we just solve for y. But this is where we arrive at the contradiction, because if we times both sides here by 2 sine y, on the left hand side we get minus 1, but on the right hand side 0 times 2 sine y is equal to 0. And clearly we arrive at a massive contradiction here, because otherwise we're going to break maths in saying that minus 1 is equal to 0. Clearly this isn't true, so therefore C has no stationary points. So C has no stationary points. Okay. So that's just that's all we need to show essentially for part A there. I think I might have dragged it out a little bit. It seems quite lengthy for just 3 marks. There might be a quicker way of doing it, but that seems to me a pretty standard, straightforward way of showing it. So let's have a look at part B here. And for part B, it's quite important that you're confident in sketching this original equation here. Okay, it'll make the problem a lot easier to see what's happening. So for part B, what we've been told is the normal to C at the point where x equals 1 crosses the x-axis at the point A and crosses the y-axis at the point B. So we're given that O is the origin, and we're asked to show the area of the triangle OAB is this expression here, okay, where we just need to find P, Q, and R. So where do we begin with this? Well, I think the easiest thing here is to try and sketch this problem. I don't know how easy it's going to be for me to sketch this by hand. I'll give it a quick go now. If it doesn't work, what I'm going to do is I'm going to put a sketch from Desmos on the screen, just so you can see what it really does look like. Okay, so let's just give it a quick go. But this could go horribly wrong. If it does, I'm going to edit the new graph in. Okay, so like I said, you need to be confident in sketching this here. Y equals arc cos a half x. Now this is between minus 2 and 2. So from minus 2, let's just say that's here, to 2. Again, let's just say that's there. What are we going to get? Well, we're going to get something that almost has like this kind of funny shape like that. I can't draw it perfectly, but it's going to look something like that. Okay, so let's just say it looks like that. Okay. Now, what we're saying here is at the point where x equals 1. So let's just say that's there. That looks about halfway to me. This here now, at this point here, the equation of the normal, so that's perpendicular to the tangent. So again, it's not perfect, but it's going to look something like this. And this is why my sketch might fail, because it should touch the x-axis first there, and then it cuts through the y-axis. So clearly, what we're looking for here is this very small triangle here, which my sketch doesn't show brilliantly, but kind of illustrates the idea. So what I'm going to do is I'm just quickly pause this now and put up the sketch from Desmos on the screen, just so you can really see what's happening. So now we've got the sketch on the screen here. This is from Desmos, and what you can actually see here now is the problem properly. What we're looking for here is this is the origin O. This point here, was this the x-axis? Point A, yep, so that's A. And then where it cuts through the y-axis, this is the point B. So what we're looking for is this area here of this triangle, okay? This right angled triangle. Now, this is why this sketch is much better than mine, because you need to understand what this triangle properly looks like, okay? So, like we just said, this is the equation of the normal, or this is the line here of the normal, and this is the point here where x equals 1. And these 2 points here, we're going to work these out in a moment, okay? So let's start by now considering the differential here, dy by dx that we took from part A. So what did we get? Well, we got minus a half all over the square root. Now, because we're going to substitute x equals 1 into this to work out the gradient at that point, what I'm going to do is I'm going to write that with the form where it was the square root of 1 minus a quarter x squared. So that's 1 minus 1 over 4 x squared. And now we substitute x equals 1. So when x equals 1, what I get then is minus a half all over the square root of 1 minus, so 1 over 4 x squared. So if x is 1, that's just 1 minus a quarter. So what I get then is minus a half all over the square root of 3 over 4. So the square root of 3 over 4, 3 quarters. And then if we simplify that here, I get minus 1 over the square root of 3. Okay, so minus 1 over the square root of 3. Now, this here isn't the gradient of the normal to see. This is the gradient of the tangent. So for the normal, we just hit the perpendicular gradient. So for the normal gradient, we should say, then this is equal to minus 1 over m. Okay, so in that case, we get minus 1 over this expression here. So minus 1 over the square root of 3. And in that case, then, we just get positive root 3. Okay, we get the square root of 3. Now here, what we need to do now is use the equation of a straight line that we know. So that's going to be y minus y1. I think I'm going to run out of room here. Y minus y1 is equal to m lots of x minus x1. And we need to consider the points that we know. So when x is equal to 1, what's y? Okay, well that's going to be y equals arc cos of a half x, where x is 1, so that's arc cos of a half. And that's going to give me y equals pi over 3. Okay, so we now can work out the equation of the normal by substituting in y. We know x is 1, and we know the gradient, root 3. So therefore, we get y minus pi over 3. So y minus pi over 3 is equal to the gradient, root 3, times x minus x1, and we know x1 is 1, so minus 1 there. Okay, so what this gives us here now is the equation of the normal. So there's two things to consider here. What we need to do now is work out these 2 points. So this point here, I'm going to call that xa. So that's x with the subscript there, a. And this point here, I'm going to call it y, and then with the subscript b, like yb. Okay. And to work out these 2 points here, these respective points, well, xa is when y equals 0, and yb is when x equals 0. Okay, so what I'll do here is I'll just clear the screen dead quick. So clearing the screen then. Again, we're just going to use now the equation of the normal that we worked out. So what was that? That was y minus pi over 3 is equal to root 3 x minus 1. Okay, so to work out xa then, we're saying y equals 0. So when y equals 0, what do we get? Well, we get 0 minus pi over 3. So 0 minus pi over 3 is equal to root 3 times, so this point now that we want for x, that's xa, this is that point here, that's xa minus 1. Okay, so we need to solve now for xa. There's probably quicker ways of doing this. I'm just going to expand here, so I get minus pi over 3 on the left hand side is equal to root 3 xa minus root 3. Okay, so now adding root 3 to both sides, what we get here is root 3 xa is equal to root 3 minus pi over 3. So let's just make sure I've not made any mistakes here. It's very easy to do. So root 3 minus pi over 3, yeah, that's fine. And then clearly if I just want xa, we just divide by root 3. So xa is equal to, so root 3 divided by root 3 is 1, and then I've got minus pi over 3 root 3 there. Okay, so I just divided each one separately by root 3. So that gives us xa, and that's that point there. So if you put that into your calculator, you'll get approximately what this is. I can't remember what it is when I worked it out, but we're going to keep this in exact form here. Now we need this point here, yb. So to work out yb, again, it follows in a pretty similar fashion. I'm just going to change my pen color just to make it clear. So yb is when x equals 0. So when x equals 0, what would we get here? Well, y is what we're looking for here. That's yb. So I get yb minus pi over 3. So minus pi over 3 is equal, so we know the gradient, that doesn't change, that's root 3. So root 3, and we know x is 0, so that's 0 minus 1 there. Okay, so in that case I get yb minus pi over 3 is equal to minus root 3. Okay, and therefore to get yb, we just add pi over 3 to both sides. So that gives me pi over 3 minus root 3. Okay, and we're almost there now with this problem here. We've got everything we need. All we need to do now is think about how we'd work out the area of this triangle. Well, this is simply a right angled triangle. Here, we've got the base here. Okay, that's from the origin O to yb. We also got this height here. So therefore, we can easily now work out the area of this triangle. It's going to be base times by the height divided by 2. Okay, so area of the triangle. Again, I'm going to clear the screen because we keep running out of room. The area of this triangle is simply just a half of base times height. So the height will just simply be from here to here, which is xa. But be careful here with the base now. So we're going from the origin down to this point here, so that's going to be minus yb. Okay, so that's minus yb. Be very careful there. So this is a half times, I'm going to use the dot here to represent multiplication, so half times xa times, that should be a minus yb. Okay, so what I've got then is a half times xa, which we said was 1 minus pi over 3 root 3. And then we times that by minus yb. So essentially what we're doing is we're just changing the signs that we had before. So that's going to be root 3 minus pi over 3. Okay. So from here now, there's loads of different ways you can get it into this expression here. Whichever way you find easiest, absolutely fine. What I'm going to do first, I'm going to expand these double brackets here. So what I'm going to get then is a half. So I've got 1 times root 3 giving me root 3. I've then got 1 times minus pi over 3 giving me minus pi over 3. We've then got minus pi over 3 root 3 times root 3. So those root 3's will just cancel, and I'm just going to get minus pi over 3 again. And then finally, we've got minus pi over 3 root 3 times minus pi over 3. So what I'm going to get there is positive pi squared. So 3 times the 3 gives me 9, so this is over 9 root 3 there. Okay. So, again, where can we go from here? I'm going to add these together here. So add these together here. So I get a half root 3. I get minus 2 pi. So minus 2 pi over 3. And then finally we got plus pi squared over 9 root 3. Okay. And the first thing I'm going to do here is factor out this 1 over 3. If I factor 1 over 3 out, I get 1 over 6. And clearly then I'm going to times everything by 3 here. That's going to be 3 root 3. This here then, that would be just minus 2 pi if you factored the 1 over 3 out. So that's going to be minus 2 pi. And then here, if you factor the 1 over 3 out, I'm just going to get pi squared over 3 root 3. So plus pi squared over 3 root 3. Okay. And again here, what can we do? So if I rationalise this part, what do we get? So I've got pi squared over 3 root 3. So if we rationalise this, I'm going to get 3 root 3 pi squared. And that's going to be over 3 times 3, which is 9, times another 3 here. So that would be 27. And then if we cancel this down, the 3 will cancel with this 27 and give us a denominator of 9. So what I get there is root 3 pi squared over 9. And now I just factor the 1 over 9 out. So what I do there is just times everything through by 9 once we factor that out. So I get 1 over 6 times 1 over 9. So that gives me 1 over 54. And we know we're on to a winner then. We want 1 over 54. So that gives me 1 over 54. Perfect. And now we just times everything here. These first two terms by 9. So 3 times by 9 gives me 27. So I get 27 root 3. Minus 2 pi times 9. Well, that gives me minus 18 pi. And then finally here, this pi squared over 3 root 3, that's the same as root 3 pi squared over 9. So in that case then, once we factor the 1 over 9 out, I just get left with plus root 3 pi squared. Okay. And that's perfect. That's exactly what we needed here. So now we can simply see what the values of P, Q, and R are. So P here is the coefficient of this root 3, which is 27. The Q is the coefficient of pi here, minus 18. And then finally for R, that's the coefficient of this root 3 pi squared, which is just simply 1. Okay, so R is equal to 1 there. And there we have it. So that's the area of the triangle OAB, giving us P, Q, and R, and the final 5 marks there of question 4. Question 5 here is a question taking a look at a second order differential equation. So we're told resonance in an electrical circuit is modelled by the differential equation. Okay, so we got the differential equation here, where V represents the voltage in the circuit and T represents time. And for part A, we're asked to find the value of lambda, for which lambda t sine 8t is a particular integral of the differential equation. So what I'm going to do here to start with for part A is just write down our differential equation again, just so we've got it as our working. We just write this down here to start with. and that's equal to cos AT. Okay, so for a question like this where we need to find a value of this case, in this case lambda, for which lambda t sine AT is a particular integral, then what we're saying here is we're going to take v and we're going to say that's equal to this expression here. Okay, lambda t sine AT. So I'm saying v is equal to lambda t sine AT. Okay, and what I want to do here now is find the second derivative. Notice this d squared v by dt squared. That's the second derivative of v here with respect to t twice. So it's the second derivative, and then we've got 64 lots of v here. So if I can find the second derivative and then add 64 lots of v to it, then we should say that this expression here is equal to cos AT. And what we should be able to find here is that we can then go on to solve for lambda. So if we find the first derivative here, v prime, what would we get? Well, you'll need to apply the product rule. This differentiation is pretty standard. I'm not going to go into massive amounts of detail to show this. I'll just show the result that you should get here. So if we're differentiating this here using the product rule, then I get 8 lambda t. So I get 8 lambda t cos 8t, and I get plus lambda sine 8t. Okay, so that's the first derivative, but notice we need the second derivative, so I now need to differentiate v prime one more time with respect to t. So I get v prime prime here, and again we need to differentiate this. Again, you'll need to apply the product rule on this part here, this 8 lambda t cos 8t. So again, I won't go into massive amounts of detail on how we differentiate this, but just applying the product rule here, what I'd get is minus 64 lambda t sine 8t, and again what we'd get here is plus 8 lambda cos 8t, and just be very careful, don't forget the lambda sine 8t here at the end. If we differentiate that, we get 8 lambda cos 8t. Okay, so what we've got here now is the second derivative. We've got d squared v by dt squared. We already had v, so we just need to times that by 64 and then add those together. And we're going to set that equal to cos 8t. And if we do that here then, we might run out of room a little bit. Let's give it a go. So the second derivative, we've already worked that out, so that's minus 64 lambda t sine 8t plus 8 lambda cos 8t plus 8 lambda, oops, have I made a mistake here? Oh no, plus 8 lambda cos 8t, and we need to add 64 lots plus 64 lots of v here. So lambda t sine 8t. Okay, and that's equal to the right hand side here, cos 8t. So that's all equal to cos 8t. So let me just double check this before I carry on, just in case I have made a mistake. Minus 64 lambda t sine 8t, yep. Plus 8 lambda cos 8t plus another 8 lambda cos 8t, yeah, good, perfect. So that's all good up to now. So what we need to do here is just start simplifying. And what you'll notice often with these kind of questions is things start cancelling quite nicely. So what I've got here, I'll just do it in a different pen colour. I've got minus 64 lambda t sine 8t, and at the other end here I've got 64 lots of positive lambda t sine 8t. So when I times that by 64, I'm going to get 64 lambda t sine 8t. This is minus 64 lambda t sine 8t, so they will cancel. So they cancel. I've got 8 lambda cos 8t plus another 8 lambda cos 8t. So when we add those together, we get 16 lambda cos 8t. And that's all equal to the right hand side. Now, these two terms cancel. That's equal to cos 8t. Okay. And from here now, hopefully you can see this is nice and easy to solve. Just dividing both sides here by cos 8t. So I get 16 lambda. This would be equal to 1 then once we divided both sides by cos 8t. So that's going to be equal to 1. So I get 16 lambda is equal to 1. And then clearly to get lambda, we just divide by the coefficient here of 16. So therefore lambda is equal to 1 over 16. Okay. So that gives us our solution to part A there, finding the value of lambda. And now for part B, we need to find the general solution. So let's just clear everything we've got on the screen so far. And then let's take a look at part B here. So for part B, we're finding the general solution of the differential equation. So remember, for a general solution of a second order differential equation like this, so the general solution, we find the general solution by adding the complementary function, so the complementary function CF and the particular integral together, so plus pi there. Okay, now we've already got the particular integral, we've worked that out in part A, we've got the value of lambda now, we just need the complementary function here. So if we go back to our differential equation here, the first thing we need is our auxiliary equation. So our auxiliary equation is given by the differential equation. So as this is the second derivative of v plus 64v is equal to cos 8t, what we do then is we take the second derivative here as being m squared. So that's m squared, and the 64v, that would just be plus 64 there. Okay, plus 64. Okay, and this can be equal to 0. Okay, so m squared plus 64 is equal to 0. Now what we need to do here is go on to solve for m. So in this case, we'd subtract 64 off both sides, so I get m squared is equal to minus 64. And from here now, this would give us a complex solution because it's equal to minus 64, so therefore m is going to be equal to plus or minus 8i. So plus or minus 8i there. Okay, so we've got the value of m. Now we just want the complementary function. So for the complementary function here, we just write this out in full. So for the complementary function, then it's quite nice and straightforward in this case. Because we've only got the imaginary part here, we'd normally have the exponential on the outside of the bracket, but because that's going to be to the power of 0, it's just going to be equal to 1, so we don't even need that on the outside. Okay, so what I'm going to get here is just something of the form a cos, and then our part here from the imaginary part, in this case it's going to be 8t, and then it's going to be plus b sine. Again, with this being a, it'll be 8t. So our complementary function, as we've just said, is going to be a cos 8t plus b sine. Again, with this being 8 here, 8t. Remember, if that was 5, for example, it would be a cos 5t plus b sine 5t. That just tells you what this value here is. Okay, so plus b sine 8t. And like we just said then, we can now easily work out the general solution by using the fact that this is going to be the complementary function plus the particular integral. So again, if we do this in a different pen color, just highlight that this is the solution then. So the general solution here is given by the complementary function, which is a cos 8t plus b sine 8t, plus the particular integral, which we had in pi a here. So if we just write the particular integral down again at the top. So for the particular integral, we worked out the value of lambda, it was 1 over 16. So our particular integral is 1 over 16 t sine 8t. Okay, so it's just from here where lambda was 1 over 16. So for the general solution then, this is going to be equal to a cos 8t plus b sine 8t. So that's the complementary function. Now we just need to add the particular integral. And the particular integral, like we just said, it is 1 over 16. So 1 over 16 t sine 8t there. Okay. And that gives us our solution there to part B, giving us the general solution. And that gives us a solution there, I can't speak anymore, to question 5. Taking a look at question 6 now, we have a question here dealing with polar coordinates and polar equations. So what we've got here is the curve C shown in figure 1, which has the polar equation r equals 2 plus cos theta. Now we're told a bit more information down below, so we know at the point A on C, the value of r is 5 over 2, so that's this point here. We know the point N lies on the initial line, and AN is perpendicular to the initial line. We've then got the finite region R, which we can see here is what's shaded. That's bounded by the curve C. the initial line and the line AN. What we want to do then is find the exact area of the shaded region R. So this is kind of pretty standard in terms of polar coordinates. You get given this kind of region here, and then we need to go on to find the exact area of that shaded region. So where do we begin with a question like this? Well, let's just start with the bits of information that we've been given. So we know at the point A on C, the value of R is 5/2. So at this point here, we know R equals 5/2. So our polar equation is R equals 2 plus cos theta. So if we know R is 5/2, we can just substitute that into our polar equation. So 2 plus cos theta is equal to 5/2. So in that case, we can now go on to solve for theta here. I subtract 2 off both sides, so I get cos theta is equal to 5/2 minus 2. So that's the same as doing 5/2 minus 4/2 here, which gives me a half. So I get cos theta equals a half. And therefore, we just take cosine inverse of both sides. So that gives me theta. That's cosine inverse of a half, giving me pi/3. So theta is equal to pi/3. And remember, pi/3 is just the same as 60 degrees. So what we can do now is we can draw this triangle here, OAN, as a right angle triangle. That's what we've got here. So this is a right angle triangle. And if I just draw that up here, we get something that looks like this. This is my right angle triangle. We've got this angle here. That's what we've just worked out. That's theta, which was pi/3 or 60 degrees. And what I want to do now is I want to work out these lengths here. And if we just think about it, if I just take a very simple example where base is 1 and I've got a hypotenuse of 2, then this length here must be √3. Okay, 1 squared plus √3 squared would give us 2. That would be √4 giving us 2. Okay, so we're going to use this as our basic example. Now, what I want is I want this triangle, if we think about it, in terms of what we've got here in the problem. So if I draw another right angle triangle, it might make it a bit clearer what I mean. Again, this would be a right angle triangle, but this time we know this length here, R, is 5/2. That's what we've been told here. The value of R is 5/2. So we know this length here is 5/2. So if you think about this now, whatever this length here is, it's double this length. So for example, if this is 1, that's double it. So that's 2 times 1. So if this is 5/2, to get this length to work backwards, we divide it by 2. So if this is 5/2, this length here at the base must be 5/4. So that's 5/4. And then if we think about it, if this base here is 1, and this is always √3, then I just times whatever the base is by √3. So if that's 5/4, this length here is going to be 5/4 √3, or 5√3 divided by 4. Don't matter which way you write that, they're equivalent. Okay, so that's our right angle triangle. Now, because it's a right angle triangle, we can easily find the area. So the area here of this triangle, so the area of OAN, that's going to be equal to the base times by the height divided by 2. So that's going to be a half of the base, which is 5/4. So half of 5/4. And then we times it by the height, which is 5√3/4. So 5√3/4. And I think the question here now comes to why are we working out this area of the triangle? And ultimately, it makes sense here for the area here, R, this shaded region. If we can work out the area of OA, CB, if I call this B here, so that's C, OACB, if we can work out this area, this full expression here, or this full shape, and we can work out the area of the triangle, then all I need to do is take the area of the full thing and minus the area of the triangle, and we've got our shaded region R. Okay, so we've partly there now. We've worked out the area of the triangle. If we just simplify this here then, what would we get? Well, 5 times 5 is 25, times by the 1, so I get 25√3 as my numerator, 25√3 as my numerator, and then we've got 4 times 4, which is 16, times that by the 2, so I get 32 as my denominator. So the area of OAN is 25√3 divided by 32. So that's the area of the triangle. we now need the area of the full expression, and this is where we now need to use our polar equation and a little bit of integration. So this is where it gets a little bit painful, but let's try and stick with it. So we're looking for the area now of OA CB. Okay, that's what we're looking for. And remember the formula here for when we're integrating with polar coordinates. So that's going to be a half the integral. We won't think about the limits just yet. We'll come back to those in a moment. But the formula here is r squared d theta. And this is given in your formula book, so you don't have to worry about memorizing this. But that's our formula. Now, r here is 2 plus cos theta. So that's going to be quite straightforward when we square it. The limits, let's think about the limits here now. So what are the limits in this case? Well, the limits just come back from our angle here. Okay. In that case, our upper limit would be this angle here, pi over 3, and our lower limit is just going to simply be 0. Theta equals 0 here. So lower limit 0, and upper limit is pi over 3. And then it's r squared. So if r is 2 plus cos theta, this is 2 plus cos theta all squared, and then we're integrating this with respect to theta. Okay. So we're on a good start with this now. We just need to keep going with this, simplifying our integral here. So we're going to expand this double bracket here. And this is pretty straightforward if we finish this off over here. So I get a half the integral from pi over 3 to 0. So what I get then is 2 times 2, which is 4. I'm going to get 2 times cos theta, give me 2 cos theta. And again, I get another cos theta times 2. So I get 2 lots of 2 cos theta, so that's 4 cos theta. And then finally, we've got cos theta times cos theta, giving me plus cos squared theta. Okay. And that's all with respect to theta. Now, this is, again, pretty standard. You will see this a lot. And often when you're integrating like this, you will need to use your trig identities at some point. Okay. And we'll see this in a moment. So if we start actually integrating here term by term, before we actually do the integration, let's use our identity here. So this cos squared theta, we can rewrite that as a half cos 2 theta plus 1. Okay, so this here, I'm going to write that as a half cos 2 theta plus 1. Okay, and then it's much easier to integrate like this. So you can just kind of skip to this step. I'm trying to make it as clear as possible so everyone watching understands what we're doing. So again, our limits are the same. We get 4 plus 4 cos theta plus a half of cos 2 theta plus 1. And that's with respect to theta. So we're running out of room here, which is a bit of a shame. I kind of want to keep this all on one screen. Let's just clear the top half and then we'll work back down again. So let's clear all this here. Okay, including my beautiful diagrams. Let's get rid of them. So this takes longer than I imagined. We're nearly there. Right, here we go. So let's carry on from here now. Right. So we've got this result here now. Now we just need to integrate term by term. So we keep our half on the outside here. So if you integrate 4 here with respect to theta, that would give you 4 theta. We've then got 4 cos theta. So when we integrate this here with respect to theta, that's going to be 4 sine theta. So plus 4 sine theta. We've then got this a half cos 2 theta. So if you think about it, that's going to be cos 2 theta divided by 2. And because this coefficient here of theta is 2, then that means we need to also divide by 2 as well. So if it's already a half cos 2 theta, or cos 2 theta over 2, what I'm going to get then is sine 2 theta over 4. Okay, so I'm going to get a quarter sine 2 theta. Or you could write that as sine 2 theta divided by 4. They're both the same. And then here, I would get a half. A half times 1 is a half. So you integrate that with respect to theta, and you get theta over 2, or a half theta. Okay, so we'll write that as a half theta. And And don't forget our limits here of 0 and pi over 3. Okay. And at this point here now, we just need to start substituting our limits in here. If it makes it easier, let's start simplifying this. So we've got 4 theta here at the front. We've got a half theta here. So that would be 8 theta over 2 plus a half theta. So that's going to give me 9 theta over 2. You don't have to do this. You can just substitute it anyway. But in maths, let's make life a little bit easier. It's already hard enough. So that's 4 sine theta. And a quarter sine 2 theta. So a quarter sine 2 theta. And we've simplified that. So 0 and pi over 3 again. And now we'll substitute our limits in here. Okay. So this is going to be equal to a half. So we've got 9 theta over 2. So we replace the theta here with our upper limit first. We're substituting in the upper limit first. So it's going to be 9 lots. Or we can write that as 9 over 2 times pi over 3, whichever way you prefer to write this. Plus for sine theta. So that's sine of pi over 3. Sine pi over 3. And then finally we've got a quarter of sine 2 theta. So that's going to give me a quarter sine 2 pi over 3. Okay. So that's my upper limit. And when we substitute the lower limit in here, with this being 0, whenever you substitute this in here, everything's going to be equal to 0. So that's just going to be minus 0, which we don't need to even write down. So that's what we get there when we substitute in the upper limit and the lower limit. So at this point now, it's just a matter of simplifying here. And then making sure we find this with the exact area. So, again, we've got a half here. Let's just keep that on the outside. Let's just start simplifying these exact angles here. So we've got a half of 9 over 2 times pi over 3. We've got 4 sine pi over 3. So remember, sine of pi over 3, sine of 60 degrees, that gives us root 3 over 2. So we get 4 lots of root 3 over 2. And then here we've got sine 2 pi over 3. So again, that's going to give me root 3 over 2 here. And then we times it by a quarter. So I get a quarter of root 3 over 2. Okay. And we're about to run out of room here at the bottom, so let's just clear all this. So we've got enough room just to finish this off down here. Just so we can do it all on one page. And let's just remove this so I don't confuse anyone. So, if we carry on here now, we've substituted our limits in from here all the way here. We've just simplified up to here. And in that case, then, if we keep simplifying, I'm going to get 9 pi over 6. So let's just start simplifying here. I've got 9 and this 3 here, so they'll cancel. Get a denominator of 1 there. This would be 3. So it's going to give me 3 pi over 2. And then we times it by a half. So that gives me 3 pi over 4. That gives me 3 pi over 4. This 4 and this 2, that becomes 2. That becomes 1. So I get 2 root 3. And then we divide it by 2. So that's 2 root 3 over 2. 2 root 3 over 2. And then here, I'm going to get root 3 over 8. So plus root 3 over 8. So let me just double check, just to make sure we've not made any mistakes. I look like I've made a mistake somewhere. Where have I made a mistake? So I'm back. I thought I'd actually made a mistake. Turns out I didn't. In case you didn't spot what I'd made a mistake on here, or what I thought I'd made a mistake on, I was multiplying this pi over here, so that gives me root 3 over 8, but I forgot to times it through by a half. So I was convinced something had gone wrong, but actually I'm just not looking properly. So that's root 3 over 16 there. Okay. And at this point here now, we just need to simplify this. So all we can simplify here is these two parts together. So that'll give me 3 pi over 4. And then we add these parts together here. And if we think about this, if I get this over a common denominator between these two parts, I need to times this by 8. So that's going to be 16 root 3 over 16. So 16 root 3 over 16 plus root 3 over 16, that's going to be 17 root 3 over 16. Okay. So now, like we just said, we just want the area, or the exact area of the shaded region R. Okay, so R. And like we said before, that's going to be the area of OACB. So that's this area here. And then we minus the area of the triangle that we worked out before, OAN. Okay. So in that case, we've got this area here, 3 pi over 4 plus 17 root 3 over 16. That was the area of OACB. So this is here OACB. And now we minus the area of OAN. Now I don't have it on the screen. We did that at the very beginning. But the area of OAN is 25 root 3 over 32. Okay. So when we actually go on to simplify this here, what I'm going to do then is I'm going to add and simplify these two parts here because they're both root 3 or multiples of root 3 here. Get these over a common denominator then. So because this is 32, this is 16. I just need to times this here, top and bottom, by 2. So that's going to be 34 root 3 over 32 minus 25 root 3 over 32. So in that case, we get the 3 pi over 4 still. So 3 pi over 4. This is 34 root 3 minus 25 root 3, so that gives me 9 root 3 there. So we get plus 9 root 3 over 32. Is it 9 root 3 over 32? Yeah, over 32. Okay. And there we have it. So that gives us our solution there. Let's just double check it before I say that's fine, because I've made plenty of mistakes here. So R equals the area of OACB minus the area of OAN. Yep. We've got our area of OACB here. And then we minus this area here, which is the area of OAN, our triangle here. That's OAN. And then 3 pi over 4 plus 17 root 3 over 16. We doubled this, 34 root 3 over 32 minus 25 root 3 over 32. And yeah, that gives us 9 root 3 over 32 there. So not the prettiest answer, but that is our exact area of the shaded region R. So that's equal to R. Okay, so that gets us our 9 marks there. And hopefully my answer isn't too disjoint, and hopefully you followed along quite nicely. So that gives our solution there to question 6. Moving on to question 7 here, which is a question on everyone's favourite topic, vectors. So 3 parts to it. Part A, we just need to find the acute angle. Part B is just showing that a point P lies on this line. And then part C is a little bit more complicated, but we'll come to that in a moment. So let's just start with part A here, and let's just see what we're actually dealing with. So question 7A. So what we've got here is a tent shown in figure 2. And then in figure 3 here, this is modelled as a triangular prism. Now the side ABCD, so ABCD, that's this side here, is modelled by part of the plane with Cartesian equation 2x plus 3y minus 4z equals 1. And then the side ABFE, so that's ABFE, so that's this side on the back of the prism here. And that's modelled with the, or modelled by part of the plane with this Cartesian equation here. So for part A, we just want to find, according to the model, the acute angle between these two sides of the tent. So what we're looking for here is this angle here, this acute angle, okay, between both sides of the tent. So to do this, what we need to do is find the scalar product between the two normal vectors, and then we just use the general formula that we know to find the acute angle. So the scalar product here between the two normal vectors, sometimes you might call the scalar product the dot product, but either way, you'll get the same answer. So for the normal here, that's going to be 2, 3, minus 4, so 2, 3, minus 4. So that's my first Cartesian equation there, 2, 3, minus 4. And we dot this here with A, 12, and 15. Okay, so A, 12, and 15. Okay. And we evaluate this now and see what we get. So in that case, 2 times 8 is 16. 3 times 12 is 36. And then finally, minus 4 times 15 gives us minus 60. So if we evaluate this here, what we get is minus 8. Okay, so that gives us minus 8. And now, what we want here is the acute angle. And the formula that we use here, remember, so it's going to be cos theta. I'm just saying this angle here is theta. call it theta, so cos theta, well, that's equal to the scalar here, that product that we've just worked, the scalar products, that's minus 8. And we divide this now by the product of the two squares of the normal. So what I mean by that is here, I'm going to square 2, I'm going to square 3, I'm going to square minus 4, add all that together, and then we times that by the this normal here. Again, we square each term and take the square root. So I get 2 squared plus 3 squared plus minus 4 squared. Okay, and we take the square root of all of that, and we times this by the square root again of this normal here. So 8 squared plus 12 squared plus 15 squared. And this here, now we just need to put this into our calculator here, and obviously take cosine inverse of both sides here to get theta. Okay, so theta here is going to be equal to cosine inverse of all of this expression here. So all of this here, you need to do that's cosine inverse. And what you should get here, make sure your calculator is in degrees here. We're giving our answer to the nearest degree. And what you should get is that theta is equal to 86 degrees. Okay, so that's our first angle there, 86 degrees. So that's part A done. Now for part B, we're told these two sides of the tent meet along the straight line AB. So this is AB here at the top. And we just want to show for part B, just for 2 marks, that according to the model, the point P, 6, 7, 8, lies on this straight line. So 6, 7, 8 here for P. How do we do this? Well, in this case, if this point P lies on this straight line, then once I substitute that into both Cartesian equations, these coordinates of x equals 6, y equals 7, and z equals 8, if we sub that into both Cartesian equations, it should be equal to this right-hand side value here. Okay, so if we sub that into the first equation, then we get 2 lots of 6 plus 3 lots of 7 minus 4 lots of 8, and this should be equal to 1. So I get 12, 2 times 6 is 12, 3 times 7 is 21, so we add 21, and then minus 4 times 8, so that's minus 32 there. So 12 plus 21 gives us 33, minus the 32 is equal to 1. So it works for that Cartesian equation. We just need to verify it now for the second Cartesian equation here. And that's going to be 8 lots of 6. Again, just substituting 6, 7, 8 in here. So 8 lots of 6 plus 12 lots of 7. And then finally, 15 lots of 8. And this should be equal to 252 here. So 8 times 6 gives me 48. 12 times 7 is 84. And then finally, 15 times 8 is 120. If we add all these together here, what you'll find is you do get 252. So that's equal to 252. And that's what we wanted to show there. So what we want to show is that when you substitute this point in P into both Cartesian equations, you get what it's equal to on the right-hand side. So all we need to give now is just a quick conclusion to this. And all we need to say then is basically, what I'm going to say here is, therefore, P lies on both planes. So P lies on both planes. So it lies on both planes, and therefore lies on the straight line. Okay, so I'm running out of room a little bit, but that's the idea here. So it lies on the straight line. And there we have it. Okay, so that's all we need to show for part B. Pretty sharp, and hopefully should be pretty straightforward. And then finally, let's have a look at part C here. So let's just clear everything we've got here so far and have a look at part C. So for part C, we're told one end of a rope is attached to the top of the tent at the point P. So remember, P is this point here, 6, 7, 8. And the other end is pegged into the ground at the point Q. The rope is modelled as a straight line, and according to the model, Q has coordinates -4, -3, and 0. And what we want to do, again, find, according to the model, the acute angle between the rope PQ and the side ABCD of the tent. So, how do we do this? It's not the easiest question, and there's a few different ways you can actually take this question and approach it. What I'm going to do here is I'm going to find the scalar product between the direction of the rope and the normal to side ABCD. That's what we're looking for here, side ABCD of the 10. Okay, and once we find that, then we can just do basic trigonometry, because what we're going to end up with here is just a right angle triangle. Okay, so well, what we've got here is the point P, 6, 7, 8, and we have our point here Q. So, like we said, we're going to do the scalar between the direction of the rope. So what I'm going to get then here for part C, if we start with the scalar product, let's keep it with the brackets here just so I make it clear. So what I've got then is 6, 7, 8. So I've got 6, 7, 8. I'm looking for the direction of the rope. So we minus here our point Q, which is minus 4, minus 3, and 0. And we dot this here now with our side here for A, B, C, D. So 2, 3, 4, this normal, or 2, 3, minus 4, I should say. 2, 3, and minus 4. Okay, so let's start with this part here in the first bracket. Well, 6 minus minus 4, that gives us 10. 7 minus minus 3, that gives us 10 as well. And then finally, 8 minus 0 gives us 8. So we get 10, 10, 8. And we dot this, I'll find the scalar product of 10, 10, 8, and 2, 3, minus 4. Okay. So in that case, 10 times 2 is 20. 10 times 3 is 30. That's a 0. 20 plus 30, and then we've got 8 times minus 4, giving us minus 32 there. Okay. So 20 plus 30 gives us 50. Minus 32 gives us 18. Okay, so we get 18. So what I'm going to do now is I'm going to find my acute angle. So what I'm going to get here is, like we just said, a right angle triangle. That is supposed to be a right angle triangle. Doesn't look fab, but that's what we've got. Got my right angle triangle here, so that means we can apply basic trigonometry. And I'm going to get two angles. I'm going to get an angle here. I'm going to get an angle here. Now, it doesn't matter which one you actually assume as being the angle that we're looking for here. If we just call one theta and one alpha. So if I call this one here, let's call that one theta. Let's call this one here alpha. Okay. So we're looking for here the acute angle between the rope PQ and the side ABCD. So what this would be here, this would be your point P at the top of the tent, which is 6, 7, 8. And this would be Q here at the bottom, call that Q, which we know is minus 4, minus 3, and 0. Okay, so my layout's not fab here. Make sure your diagram's a little bit neater than mine, but that's essentially what we're looking at. So what I'm going to do here now is find the acute angle here using this 18. And then once we find that first acute angle, we're just going to do 180 minus 90 minus that acute angle and get the remaining angle. That's what we're just looking for here. Okay, and obviously making sure we give the answer to the nearest degree. So what we'll say then is cos theta. So cos theta is going to be equal here to 18. That's what we said here. This is our scalar product, so it's always the scalar product 18. Well, it's 18 in this case. We divide it by the square root of each normal squared. So it's going to be 10 squared. So we get 10 squared plus 10 squared plus 8 squared. And again, we multiply this by the other square root of 2 squared plus 3 squared plus minus 4 squared. Okay. And I need to just evaluate this on my calculator. Again, we need to take cosine inverse of this. We just want the value of theta here. So I'm assuming you're okay with this, just to find theta. What you should find here for theta is that this is equal to 78.1. Okay, so we get 78.1 degrees there. Okay. So we get 78.1 there. And what we're looking for now is just this remaining angle here, alpha in this case. Okay. So we've got our first angle. We just need our remaining angle. And again, this is just simply a matter of now of taking 180 degrees, it's a triangle, minusing the 90, and then minusing this angle here. So therefore, we just change pen colour. So therefore, we're going to do 180 minus 90 minus 78.1. And what we're going to get here is 11.9. So make sure I've got this on my calculator. 11.9 degrees. But we want to give our answer to the nearest degree. So therefore, the acute angle is going to be 12 degrees. So the acute angle between the row PQ and the side ABCD of the tent is 12 degrees. So let's just write that there. Acute angle between PQ and ABCD. Okay, and there we have it. So 12 degrees. My diagram might not be perfect. It might be the other way around. I've not really read into this problem too much, but that's essentially what you're looking at. You just get a right angle triangle like that. Okay. So if you do notice any mistakes, I might have made a slight mistake somewhere in this question. I don't think that's anything wrong with the actual workings. All these do match up correctly, but my diagram might be slightly off here. But either way, you should get this. And like I said, there is a few different ways of tackling part C. You know, so if you do it in a different way and you think your way's better, just leave a comment and tell me which way you've done it. So that gives our solution there to question 7. And finally, we arrive at the very last question here on our Core PO2 predicted paper, and this is a question on volumes of revolution involving de Moivre's theorem. Now, this question might look a little bit different, and that's because I've had to actually create it myself. So forgive it if it looks a little bit, you know, a little bit less neat than the actual exams, but hopefully it will still give you a bit of good practice. So this is a question I've had a lot regarding the volumes of revolution question. This is probably what it's going to look like. So in part A, that's where you use de Moivre's theorem, and then in some part, I imagine it would just be a part B here, you have to link part A and B together. Okay, so part A is where we use de Moivre's theorem, and then in part B, it's just using what we found in part A to go on to find our volume of revolution. So let's start with part A here first, which is just looking at de Moivre's theorem. So what we've been told here, or asked to do, is by writing a suitable expansion for cos 5 theta or otherwise, show that cos to the power 5 here theta is equal to 1 over 16 times cos 5 theta plus 5 cos 3 theta plus 10 cos theta. And this is for 3 marks. So like I said, this is what you're probably going to get just to start with here. And hopefully this part here should be relatively straightforward, just using de Moivre's theorem here to get this result. Now what I'm going to do here to start with is, in this case, we're looking for cos, we're starting with cos 5 theta here, and we want to show this result. So what we start with here is, remember, z to the n plus 1 over z to the n. Well, remember, this result here is equal to 2 cos n theta. Okay, now we can use this result here to find, for cos 5 theta, this result, and show this is true. So what I do then is I take z plus 1 over z to the power of 5, because we're looking for cos to the power of 5 here. So that's the power of 5. And that would be the same here as taking this result to the power of 5, where n equals 1. This is z to the 1 plus 1 over z to the 1. So this is 2 cos, so n is 1, remember, so it's just 2 cos theta to the power of 5. Now it's up to you how you expand this left-hand side here. I would just recommend using binomial expansion. That's how I do it here. Some people's calculators can do stuff like this. If your calculator does it, that's fine as well. But just by using the binomial expansion, I'm not going to go into how to do this, just to save time. But what you should get here using binomial expansion on this part is z to the 5 plus 5z cubed plus 10z. And then we get plus 10 over z, or z to the minus 1. I'm going to write everything in index notation. Plus 5z to the minus 3. And then finally, plus z to the minus 5. And this is all equal to the right-hand side here. So if we take 2 cos theta and raise it to the power of 5 here, well, 2 to the power of 5 is 32. So it gives us 32. And then cos theta to the power of 5, that's just simply going to be cos to the power of 5 theta. Okay? And this looks perfect up to here now. And the reason this is kind of what you should be looking for here is, notice I've got these pairs now. So I've got z to the 5 and z to the minus 5. I've got 5z cubed, 5z to the minus 3, and I've got 10z and 10z to the minus 1. This is exactly what you should be looking for here. Okay, if you don't get something that looks like this, something's probably just gone wrong with your expansion. So what I do now is just literally what I've just said. We pair the connecting parts together. So I call the connecting parts z to the 5 plus z to the minus 5. I've got 5z cubed and 5z to the minus 3. And then finally 10z and 10z to the minus 1. And again, this is just equal to the right hand side here. 32 cos to the power of 5 theta. Okay. And remember here now, like we just said, so z to the n plus 1 over z to the n, that's 2 cos n theta. Okay. So now we've got z to the 5 plus z to the minus 5. So if we just do that over here just so we can make it clear what we're doing. So z to the 5 plus z to the minus 5. Well, that's just the same as what we've got here, where n equals 5. Okay, so that's going to give me 2 cos, where n is 5, so I get 2 cos 5 theta. Okay, and we just need to do this now for each pairing. So my next pairing here is 5z cubed, so I've got 5 lots of z cubed plus z to the minus 3. So that's going to be 5 lots of 2 cos, and in this case n equals 3, so that's going to be 3 theta. Okay, and then finally we've got 10z and 10z to the minus 1, so this is my final pairing here. So that's going to be 10 lots here of z, so it's z to the 1, so we just write z plus z to the minus 1. Okay, and again here that's just going to give me 10 lots of 2 cos theta. Okay, so we've got all our preliminary work in there now. All we need to do is just put everything together here. So if we just put everything back into what we've got here now, we've got 2 cos 5 theta. We've got 5 lots of 2 cos 3 theta. So just multiplying 5 by 2, we get 10 cos 3 theta. So plus 10 cos 3 theta. And then finally, 10 times 2 gives us 20. So we get 20 cos theta. And this is all equal to the right hand side still, 32 cos to the 5 theta. Okay. And from here now we're pretty much done with this question. We need cos to the power of 5 theta, so we don't need this coefficient here of 32. So all I do now is I divide through by 32. So therefore, what we get then is cos to the 5 theta here is equal, so that's going to be 2 over 32, which would give us 1 over 16. So we get 1 over 16 cos 5 theta. I've now got 10 cos 3 theta divided by 32, so that's 10 over 32. Again, I'm going to put everything over 16, because notice here it's 1 over 16. They factored that out, so I'm going to get everything over 16 here. So that's going to be 10 over 32, which is the same as 5 over 16. So plus 5 over 16 cos 3 theta. And then finally, 20 over 32, that's the same as 10 over 16. So I get 10 over 16 cos theta. And then finally, just to get it in the very exact form that they've got here, all I need to do now is factor 1 over 16 out. So factoring the 1 over 16 out, we get 1 over 16. That's going to simply give me cos 5 theta. So we get cos 5 theta. That's going to be 5 cos 3 theta, so 5 cos 3 theta. And then finally 10 cos theta, so plus 10 cos theta. And there we have it. So that's the result we needed to show there for part A. So that's cos to the power of 5 theta. Okay, so that gets our first 3 marks. Normally if you see these kind of questions as a Moivre's separate question, it's normally about 4 or 5 normally for these kind of questions. So a little bit less than you might be used to. But the majority of the marks we're going to find now for part B. Okay, so even if you can't actually show that result, you can still go on to do part B. So don't read too much if you find Moivre's a bit tricky, or you panic on the day. You don't need to read too much. Okay, so that's part A done. Let's have a look at part B now. And part B, we've got this beautiful diagram that I've put together here. It doesn't look quite as neat as the actual exams, but what we've got here is the curve in the diagram. So this is x equals cos squared y times the square root of cos y. And the finite region is bounded by the curve, the y-axis, and the line y equals 0. And that's shown in the diagram. So this is this grey region here, okay? Now we're told the region is rotated through 2 pi radians about the y-axis to form a solid of revolution. And all we want to do for 6 marks here is just show that the volume of the solid generated is 8 pi over 15. So, like I said, even if you couldn't do part A, you can still go on to do part B, and I would imagine that's going to be true for the exam question on Corpio 2. So, where do we begin? Well, the first thing we've got here is x equals, so let's just write this down as part B, x equals cos squared y times the square root of cos y. Now, we know the formula here for finding a volume of revolution like this. So, as we're rotating this 2 pi radians about the y-axis, then the volume here, V, is going to be equal to pi times the integral of x here squared. So, x squared dy. Okay, and obviously our limits here depend on what we've got. So, we're going to be integrating here from 0. So, 0 is our lower limit, and our upper limit will be pi over 2. So, pi over 2. So, how does this connect with part A here? Well, it's not immediately clear, and if you do struggle to kind of find the connection, just carry on as if part A isn't there. And what you should find at some point is they do connect. So, if we take x here and we square it, that would give us x squared. So, x squared here, we're going to square both sides. So, if I square that right-hand side here, that's cos squared y times the square root of cos y. And we square this result here, well, what would that give me? Well, that's going to give me cos to the power of 4y. So it's going to give me cos to the power of 4y. And then the square root of cos y, we square that, that would be cos y. So what I get here is cos to the power of 4y times cos y. And in that case, just simplifying the powers here, this gives me cos to the power of 5y. Okay? And hopefully now you can spot the connection. So between part A and B here, the connection is that we're going to use this result. So cos to the power of 5 theta. Obviously they're doing it in terms of theta. Doesn't matter too much. We're doing it in terms of y. Obviously we just change any thetas to y. Okay. So therefore, using our formula here for v, so v is going to be equal to pi times the integral from, again, 0 to pi over 2 of x squared. And x squared, like we just said here, is cos to the power of 5y. So cos to the power of 5y. And again, we integrate here with respect to y. So dy. And at this point here now, we're on to a good start. All we need to do now is just use our result here in part A. So replacing here our cos to the power of 5y here with our result in part A. And what we get is we're going to get pi. Now, because this is 1 over 16, and then it times is by everything in the bracket, that's just a constant here for each term. So I'm going to take that constant outside. So because this is pi, if we times it by 1 over 16, I'm going to get pi over 16. So on the outside here, the integral, we're going to get pi over 16. You can keep it in the inside if you want. I just prefer to take it outside if possible. So that's all I'm doing here. And this is v. So then we times this by the integral from 0 to pi over 2. So it's going to be 1 over 60, we took the 1 over 16 out, so ignore that. It's going to be cos 5y. So cos 5y plus 5 cos 3y. So again, this is why I'm saying you don't even need to be able to do part A. They give you this to kind of guide you. So finally we get plus 10. So plus 10 cos y. Okay? And this is all with respect to y. So all we need to do now is go term by term. Forget the limits for now. Let's just integrate each term as we go. So here, what am I going to get? Well, when we integrate cos 5y here, that's going to give me sine 5y, but we divide by this term here, this constant. So because that's 5, we're going to get sine 5y. So sine 5y divided by 5. Moving to the next term here. Again, they're all in terms of cos. So when we integrate, it's quite straightforward. This is 5 cos 3y. So when we integrate this here then, that's going to be 5 sine 3y. 5 sine 3y, yep. 5 sine 3y. And again, we divide by this constant here, which is 3. So we get 5 over 3 sine y, or sine 3y, we get mixed up here. And then finally, 10 cos y. If we integrate that here with respect to y, that just simply gives me plus 10 sine y. So plus 10 sine y. Okay, so before I carry on here, let's just double check I've not made a mistake, because I usually do. So integrating cos 5y, sine 5y over 5, perfect, divided by the 5. 5 cos 3y, so we're going to get 5 sine 3y, divided by the 3, perfect. And then finally 10 sine y. So all looks good up today. We have annoyingly run out of room, which is usually the case for when I'm doing questions. So what I'm going to do here is I'm just going to try and erase everything up here. That wasn't meant to happen. Let's try again. Why did that happen? Here we go. So let's try again. Right, so let's just get rid of this up here and try again. Okay, so we nearly got there without any professional errors. Let's give it a go. So all we need to do now is substitute our limits in. Okay, and then we're going to times everything by pi over 16. So this is all times by pi over 16, which I've run out of room. So I'm just going to plonk it there. Okay, so pi over 16 times everything once we put our limits in. So when we put our limits in here, again, we times everything by pi over 16. Now, putting these limits in here, the limits are actually quite nice for this question. So when I put pi over 2 in here, so that's going to be sine of 5 lots of pi over 2, and then we divide it by 5. So my first result here is going to be 1/5. So we get 1/5 there. When we substitute pi over 2 into this part here, 5 sine 3y over 3, well, that's going to give me minus 5 over 3. So we get minus 5 over 3. And then finally, 10 sine y, substituting pi over 2 in here, then we just get plus 10. Okay, so that's for the upper limit, pi over 2. And the good thing about this question is when you actually substitute the lower limit in here, each result works out as 0. So that's 0 plus 0 plus 0. So we minus 0. So it doesn't change the result here. So what I get then is pi over 16 times this result. And from here now, we just need to simplify this. So 1 over 5 minus 5 over 3 plus 10. Well, that gives me 128 over 15. So I've got pi over 16 times 128 over 15. Okay. And all you need to do here now is just literally put this into your calculator or divide it by hand. But what you should find here is you get 8 pi over 15 there. Okay, which is exactly what we wanted to show here in part B. So we were looking to show the volume of the solid generated is 8 pi over 15. And there we have it. So that gives our solution there to part B. And hopefully it wasn't too tricky, and hopefully I've not made a mistake with the question, because I have just done it kind of by myself. I've not had anyone check it, so you know, it might not be perfect, but hopefully it has helped, because I did get a lot of questions asking about that. But there we go. So that gives us our solution to question 8 and brings us to the end of this Core Pure 2 paper. So like always, I'm happy to hear feedback, how people find the paper. As I mentioned at the very start of the paper, it's not always possible to fit every question that's mentioned on the advanced information based on how Edexcel write their exams. I can't do that using the topic tests and old exam questions. It's not quite possible because I'm not writing the questions myself. But hopefully you still find this helpful. So yeah, so good luck in your exams and cheers.